are at 125, and we've got a big, long chapter here called Security Engineering. We did a little bit of it last time. We'll do some more this time, and the rest next time. And so you should turn in your topic, which is just a few words of your security topic you're going to do a presentation on. And the presentations start next week for the early ones, and in 2 weeks is when most people should have your presentation ready. It's only 4 minutes long. And one thing I always get in this class is people turning in like a PowerPoint file, and that is not the point. The point is you have to actually present it in class. Turning in the PowerPoints is not sufficient. You just have to actually give the presentation, but I will ruthlessly limit you to 4 minutes. So trim it down or you'll get cut off partway through. But it's the same thing as lightning talks at conferences. Yeah?
When do we have to say whether or not we're ready for next week?
Oh, when class starts. When class starts, I'll say who's ready today and just get a list, yeah. And so usually in the early day, there's only a few people that want to do it, so I can have a lecture that day. And the day when everybody's presenting it, I have no lectures. We have enough time for everybody. And people that want to do it late can do it late. They just lose some points. Yeah, good. Can we upload it as YouTube? Yes, you can. You could record a YouTube and upload it, make it 4 minutes long. That would be fine. You can also do it remotely over Zoom, live, or you can do it in class. And good. And you don't actually need to use any slides at all if you want to. You can just be completely verbal if you like. Some people like to do that, but most people prefer to have some visual aids. But all I want to hear is a clear explanation of some security topic, just to show that you are able to communicate well. That's the point. Good. So here I've got these slides. All right, so we're talking about models. And last time we talked about Biba and Bell LaPadula and Clark Wilson and the other models. And here's some more models that are used to understand security setups, security enforcement in computers. So the information flow model are ones that limit how the information flows, and Bell LaPadula and Biba both use that. They control security by limiting how information moves from one area to another. Then there's the Chinese wall. Did we talk about this last time? I think we did. Okay, Chinese wall originally was for law firms. If your law firm would take a case, and then you would take a case for the other side, now you're representing two different conflicting parties, so they developed this thing called a Chinese wall, where you would have certain lawyers here and certain lawyers here, and they're not supposed to talk to each other at all, and you supposedly maintain a separation of information. That's one way to avoid conflict of interest. Non-interference is a security property that is desirable in any security network. It is in fact very difficult to achieve, but the point is that anything at, say, a top secret clearance should have no effect on information at an unclassified level. That is the point. Whatever goes on at a high security level should not in any way be observable, even indirectly, from a lower level. One famous example of this is, it's a well-known technique that if you want to know if the United States is planning a major military exercise, all you have to do is order a pizza in Washington, D.C. And all the pizza shops will be backlogged because they make all their staff stay late, they all order pizza. And so just by seeing how many pizza orders there are at like 7 at night, you can tell if the military is doing something major. And this is like we watched the troop buildup on the Ukrainian border before Russia invaded with satellites, and we knew they were going to do it because you could just watch the troop movement, you can't hide it. And so something at a high security level has something you can observe without that clearance indirectly. And this is a failure of non-interference. Non-interference means that whatever happens at a high level has no effect on what's going on at a low level. And that is actually quite difficult. For example, a cryptographic key, which is a secret, can be found by measuring the power consumption, which is not a secret. And that's the problem. These things are called covert channels or side channels, where some data is leaking out unintentionally to an observer who doesn't have the right clearance. And now here's another type of model, the take-grant model, where you can take, grant, create, or remove permissions, and you can have a complicated model of who can do these things. So here you've got Alice, who has access to secret documents, and Bob and Carol. Bob can take away Alice's permission. Alice can grant permission to Carol to get there, and on it goes. And so there are rules of who can take permission, who can grant permission, and who can create, CNR is create and remove, I think. Yeah, who can create and remove records. All right.
That's a database.
Yeah, well, you can use it for a database or files or any kind of computer record. And in a way, this is kind of like a normal Windows machine where you have an owner of a file. and the owner can decide who else can get in there. You can choose to share your files or not to. It's not technically called a take-grant model, but it does have some similarity to this. And so this is the access control matrix, which you will see in a Windows machine. You have a set of users, and then you have whether they can read or write or have no access to a file and applications and so on. And then there's something called the Graham-Denning model, where you have subjects, objects, and rules. And here's various kinds of rules: transfer, grant, delete, read, create, destroy. You can see these are all just many, many ways of doing the same thing, of just limiting the various things you can do and who's allowed to do it. And someone says, does that mean if Uber or Lyft want to know who is who without a specific client's name, it can do? Well, yeah, that's a similar issue, Zhu, where they talk about this when you anonymize data, like a search history. They anonymize it by not putting your name on it, but in fact you can deduce whose it is by looking at the neighborhood where they query for restaurants and things like that. Yeah, so I mean, you can often deduce information that you did not want to disclose from the information that is disclosed. All right, and so this is the HRU model. Again, very similar, it just has a different list of objects, of actions here. All right, and then we can talk about modes of operation. This is the military concept from the Department of Defense, and there are 4 modes of operation for a system: dedicated, system high, compartmented, and multi-level. These are ways to set up the technical computer systems that are going to handle classified information. The safest and most expensive and most difficult is dedicated. You have to have separate computers for every level. Everything's separate, an air gap between them, and this reached the point where some people had 7 computers on their desk. You had to have one computer for top secret and one for secret, one for classified, one for unclassified. There were other categories, and that's one way to do it. And I had a student in my classes who worked at a investment company, and they had a simple way to prevent themselves from getting hacked. All the computers, their entire network was not connected to the internet at all. The only machine in the room that was connected to the internet was one Mac in the break room for people to use on their break, like go to Facebook, and then you'd go to work and everything, just type in stuff and process it, and it would not connect to the internet at all. That was how they protected their network. And that's an air gap. All right, system high is where your system can contain objects of mixed labels, but all subjects must be cleared up to the highest object. So you might have multiple security levels of information on a machine, but all the people that use it must be cleared to the highest level on that machine. So that's not as expensive as this one here, dedicated, but it's similar. And then you got compartmented, where everybody has to have the necessary clearance, but they don't have the formal access approval, and they're placed in compartments, and you have technical controls to enforce the need to know. So the horizontal controls, as well as the vertical controls, are technically enforced. And the cheapest one, and most dangerous, is multi-level, where you have people with multiple levels of security clearance and data of multiple levels of security clearance all in the same machine. And you trust the operating system reference monitor to keep track of this all. Make sure it knows who you are and what your level is and what level is required for everything. And of course, this is what you have at a corporation. You have like one domain controller, one file server with all this stuff, and you have a set of permissions and group policies that supposedly make sure that only the authorized people can get to things. All right. And I say this is only allowed if you have a reference monitor which controls the access. How does a server collect or transfer of data work if an air gap not connected to the internet? Well, the only way they'd be able to move data in or out would be typing it or putting it on a USB drive and moving it to another machine. It's mostly done with USB drives. And that's how we infected Stuxnet. The uranium isotope separators in Iran were air-gapped off the internet, and so we and the Israelis got together and made the Stuxnet virus, which would travel on USB sticks so that it infected it and destroyed it, even though it was not connected to the internet. And that bank I described would also be vulnerable to the same thing. You have to have some way to move in the data, and you just have to make malware that will go through that, but that's much more difficult. Your risk is much lower than actually being connected directly to the internet. There are ways to go across an air gap, though. Nothing is perfect. So then we got methods of deciding how secure your system are. And so the original one was TCSEC. This was the Orange Book developed in the 1980s. the U.S. military one. Then ITSEC and Common Criteria are international models that came later. The standard that sort of defined the terms was this one here, the Orange Book. There was a rainbow series of colored books made by the U.S. military, and this was the Department of Defense Trusted Computer System Evaluation Criteria in the 80s, and part of National Institute of Standards with the NSA, and it rated your security from A to D. So you had D was essentially no protection at all. C is discretionary protection, which is what you have in typically a home computer. You have objects, and there's an owner, and the owner at their discretion can decide who to share the object with. Then you have mandatory protection, and then verified protection. And this is the same thing you're going to hear over and over in many layers here. First you have no control, then you have some organization, then you have strict organization, and at the highest level you have management managing it, making sure it stays good and checking to make sure it's working. That's verified. All right, and yes, I see someone asking, yes, all the students in any of my classes can attend class through Twitch instead of coming to the classroom. Attendance is optional in all my classes. All right, so then there was the Red Book, which did the same thing for the network, not just the storage, the computing system. And ITSEC was the European one, which was the European equivalent of the American system. So it separated functionality and assurance. Functionality is just how well the system works, and assurance is the ability to evaluate the security of the system. So it's a little bit more complicated, and you had rated it from E0 to E6. And E0 is inadequate, no security at all, and E6 is a formal model, where you really have strict management of the security, and they approximately match up. So, the lowest D of E6 is E0, and A is up here at E6. And they have other specialties like high integrity and high availability requirements and so on. The European model has a few more special cases than the older American model. And both of those are now considered obsolete and replaced by International Common Criteria, which is, has a thing called Target of Evaluation. I put an L in there if I could reach, all right, which is the system being evaluated, and a security target is a document describing the target of evaluation, the requirements in the environment. So you have a protection profile that specifies what you're trying to accomplish, and an evaluation assurance level, which is its score. So it amounts to about the same thing, but it is considered the most modern technique. And so you have functionally tested, just means it does what it's supposed to do. Structurally tested, I think means you've looked at the components in there, methodically tested and reviewed, semi-formally designed and verified, and then formally verified, designed and tested. And this is part of why you hear scandals where the military has to pay $700 for a hammer, because to get something at these high levels, they have to have a ton of management. You make a product, and you have a blizzard of paper, and bureaucrats pushing paper around and filling out forms to consider everything about that product and everything about the components that went into it, and so on. And this is just more and more concerning now after the SolarWinds attack. Everyone is really worried about the supply chain. You really should know not only what you made and whether it worked, but where all the components came from, and where all the software came from, and where all the libraries in the software came from, and whether they're all really up to date, which is a pretty monumental task, but that's where we are because of the SolarWinds attack, where the Russians actually poisoned the real supply chain. So you put on the authorized update from the right manufacturer, and you were getting owned by Russia. So now that placed nobody really knows what to do about it. They're developing systems now to try to cope with that threat, and that's going to be a hard one. Normally you say, just make sure you're really getting the update from the manufacturer and you can trust it, but if you can't do that, then we're trying to figure out what to do. All right. Okay. Hello, I. Anyway, so, all right. Let's take a look at a Kahoot 3B, which is here. All right. Yeah. All right. There it goes. Yeah, I set up this, making it so people could attend remotely just to save the students time of commuting and stuff, but it turned out to be a good thing when COVID hit. Not only was I ready to teach from home, but now that I'm here, the COVID risk is low because there's very few students in the classroom, so it turned out to be a good thing. Russian threat. Can I elaborate? Oh, this was, that was the SolarWinds attack. Happened a couple of years ago. And I talked about the Russians actually hacked into SolarWinds, which made a remote access client used by enterprises, and they modified the code on their servers. So the official updates from their servers included a Russian Trojan. And everybody, when they put on their updates, they were now under remote control of Russia. It affected thousands of American big corporations, and they probably haven't got rid of them yet. Because of course, once they're in, they are not going to just stick with that one foothold. They're going to spread and put more malware on your system. And even if you remove the SolarWinds later, that doesn't really mean you got rid of them. So what happens when you use Kaspersky and malware? Well, the problem with using Kaspersky is that when it finds something that looks suspicious, it sends it back to Kaspersky, which went to the Russian government. That's how they stole the NSA's tools. A contractor put them on a machine with Kaspersky antivirus, which was a violation of policy, and Kaspersky detected it and forwarded it and sent it back to Russia, and the Russian government took it off Kaspersky's servers. So that's when the US government banned using Kaspersky on government and military computers. And now we've moved to banning Chinese stuff on our computers and our Chinese hardware on our routers and 5G and stuff for the same reason. We really shouldn't be using stuff that comes from hostile nations on our military or government machines. It's inviting an attack.
Kaspersky was the one that tied SolarWinds hack to Russia.
Yeah. They had the same thing all antivirus does. If it detects something malicious and it doesn't recognize it, it will send it back to the company for analysis. But someone put military hacking tools from the NSA on a machine with Kaspersky, which they shouldn't have done. And so, but they said, now that you mention it, we shouldn't be running antivirus from Russia on American military machines. That's insane. You don't run a product with root permissions on your machine that comes from a hostile nation. That's obviously a poor plan. Anyway, it's too bad. Kaspersky is very technically good, but you can't really run something from a hostile nation, especially now that we're practically at war with Russia. Anyway, I guess we're ready. Let's give this stuff a shot. All right, so what feature prevents a covert channel? And yeah, two apart. I think it's only forbidden for government-related machines in America, but it's not recommended for anybody. And that's non-interference. Non-interference means that activities at high clearance, at high security levels will not affect things at low security levels. All right, what operation mode enforces an air gap between each security level? Yep, that's where you have to have dedicated hardware for every level, the dedicated model. The most secure and the most expensive and difficult to use. All right, which mode uses a reference monitor to control access? Okay, that's the multi-level. Because you have multiple levels of security on the same box, the reference monitor is the software that is supposed to keep everything correctly separate. All right, what TC-SEC level does a home Windows machine fall under? Okay, it's C. Now, D was MS-DOS. MS-DOS on fat partitions had no permissions at all. Physical access to it meant you could do anything just like a paper book. Now, Windows now has NT permissions, so only the owner can get at the files and another person would not have access to all the files. You have discretionary access control. The owner of the machine can choose to share or not share objects, and that's level C. The higher levels require actual management, higher levels of authority overlooking what you do. All right. And what's the modern international standard security evaluation method? Yep, common criteria is the new one. All right. So, all right, that's faces. Wuhan, good. And go, okay. All right, good. So, let's go back to here. All right, so, good, 6:30, we're fine. All right, so secure system design. Here's some more properties. Layering is a fundamental issue of all modern systems. When I first bought computers in 1970s, there was not layering, so you would buy a word processor and you would have to buy a printer that word processor could talk to. And if you bought a different printer, you would have to buy a different word processor that could talk to that printer. And this was, of course, ridiculous. And so layers are what prevents this. You have printers and a printer driver, so any printer can print with any word processor. You separate the components. And so anyway, there's layers at one. That's why you have to have layers of functionality so you can have interchangeable parts for different. So you have hardware, kernels, and device drivers. The kernel is the part of the operating system that controls the hardware, and the device drivers are the pieces of software written by the people that made your devices, like printers and keyboards and mice, to connect it to the kernel. And then you have the operating system, which provides a series of API functionalities, so applications you might use, like a web browser and Microsoft Office, can get to the hardware. And this layering means you can have an application that's written that doesn't have to worry about what's going on below it. It just has to trust Microsoft to write the kernel, and then you can write a word processor, and you don't have to know anything about this except how to use it. So that's the plan. And so one common feature of this is abstraction, where you do not need to worry about details. The user just sees an icon. Like, you just see a picture of a folder, you double-click the folder, in there are some files, you drag them around. You don't need to know about the sectors and clusters and directory and all that stuff on the disk. You don't see IP addresses when you send email. It just takes care of that without you seeing it. That's abstraction. So security domains are groups of subjects and objects with similar properties. And so one big division in your machine is kernel mode and user mode. Kernel mode is a mode of the processor that has full access to all the processor's instructions, including the ones that directly send signals to hardware. And that's the user mode. Everything that you launch after logging in does not have that privilege. You only have a limited amount of machine language operations you're allowed to use, because they don't want you just crashing the operating system entirely, so the machine will stop. So if you run an application and it's buggy and it crashes, it will stop, but the whole machine will not stop, because you don't have access to the kernel. You can't crash the kernel. Yeah?
Yeah, okay, you saw this code. So how about the kernel user? The kernel user is in user mode, isn't it?
Well,
the root user, sorry, the root user.
no, the kernel happens before you log in.
I meant root, sorry.
Right, oh, root. Root is still just user. Yeah.
But it has the permissions are turned off for root.
Root, if you have root or administrator, you can push kernel objects in, like loadable kernel modules and load drivers.
But from the outside.
But from the outside. And you can also, make API calls that call kernel routines. You can interact with the kernel in some limited ways through special features available for that. But if you launch a process, it doesn't launch in kernel mode. There are ways to do it, though. There are ways, of course, you have to have some way to access the kernel, but normally you only modify the kernel by rewriting the boot up process. Anyway, so this is enforced by the processor and the motherboard in 4 rings. All modern machines have these 4 rings, ring 0, 1, 2, and 3, but 1 and 2 are never used. They were used by some really old system, I think called Minix, that went out of use. All modern operating systems use only ring 0 and ring 3. So the kernel is here in kernel mode with all privilege to do everything, and the users are out here in ring 3 with the smallest amount of privilege, and that's it. Now, there is, of course, virtual machines. Now, the earliest virtual machines ran slower than normal machines because they were running on a program and they wanted them to run faster, so they introduced hardware-assisted virtualization, like Intel VT and AMTV, and this people call up like ring -1. This is a mode that lets software in the virtual machine directly contact the hardware without passing through a translation layer. And so that's most modern virtualization requires this because it makes virtual machines run very fast, and VMware claims that their virtual machines will run at 100% the speed of a machine installed on the bare metal because of this, if you have a machine that supports these hardware-assisted virtualization features. And I don't know if it's true, but it's very good. What's the difference between root access and kernel? Root access is a user that has full permissions, but kernel code is code that is running with permissions in a different mode of the processor. And you don't normally launch anything in that mode. You have to use special utilities to get there. So it's similar. What will Docker be in? That's a very good question. As far as I know, now I'm not completely up to this, at least as up to 2 years ago, you always had to run Docker as root. And your Docker images had access to files on the hard disk and vice versa. So there's a persistent statement saying that Docker is less secure than virtual machines. Docker is not as isolated. Docker containers are not as isolated as virtual machines. That's why they're smaller and faster and cheaper. But they always warn you they're not as safe. There are escapes, but you normally have to run Docker as root. And it's a...
So at what level are the antivirus running?
It's a very good question. The antivirus has a problem, right? The antivirus really wants to run in kernel mode. The problem is it's difficult to do. So what antivirus and firewalls did until about 2010 was they would hook in by modifying the system set descriptor table in the kernel. So they would replace kernel routines with modified kernel routines. That's how antivirus loaded, and Microsoft really didn't like that because that would cause the blue screen of death and kill the box when anything went wrong. And so Microsoft changed the rules around 2012, and I don't really understand how they work anymore. They made it more complicated, how you can interact with the kernel with software like antivirus, and the same thing is true of rootkits, malware. I don't understand how the modern ones work. I've been trying to add them to my malware analysis course for a while, but I haven't figured them out. It is actually a huge problem. Antivirus needs to have access to the machine at a low level, and Microsoft wants to keep everybody out of the kernel except them. And so there's a push back and forth. There's even lawsuits about it and such.
So the hypervisor running at -1.
Yeah, the hypervisor has...
If the virus get out the hypervisor, then...
Yes, you're right. In principle, if the hypervisor has enough privilege to infect the operating system, and there are some VM escape attacks, but not very many. There's many more Docker escapes than VM escapes, but both of them, they try to patch them. But Docker is a very new technology and not considered as secure. VMware is pretty secure, although it has flaws. Right now, the enterprise class VM machines are getting hacked like crazy. There's a serious problem in ESXi. So it happens.
Because those VM machines are in the cloud, so...
Yeah, that's right.
That's what the cookies are.
Yep, they do get hacked in the cloud. And so anyway, what the antivirus software on Apple iOS doesn't have the same privilege level as Mac OS. That could be. I don't really know much about antivirus on the Mac. Anyway, right, so there's open systems, are systems where it's not a secret. The specifications and all the chips and everything are open. That was IBM. IBM made it completely open about the PC, and then they got hosed because their bureaucracy was so slow, it took them like 9 months to ship anything, and independent people would just make machines that were faster and better, so they lost all their money. They never made any money on the PC. Apple has the alternative. They would remove the serial numbers from the chips, keep everything a secret, so nobody could build a Mac except Apple. And that was their closed system model. Every app has its own container. They cannot communicate with each other. That's what True of Heart says. It sounds right, but I haven't looked into that. All right, so then there's secure hardware. The system unit is the computer's case, and then there's the motherboard. This is the main board that contains the chips that you don't change much, like the CPU and the RAM, firmware and peripheral slots where you plug in things like the network card and so on. And so you have a computer bus. You've got the CPU, which contains an arithmetic logic unit and a control unit. And then you have the RAM, the hard disk, the keyboard, mouse, display, and CD, and there are communication channels in here called buses, where one component can talk to another. And so those are data buses. Now, the modern systems have North Bridge and South Bridge. The North Bridge bus is the high-speed bus where it lets the CPU talk to RAM memory and video memory really fast. So you can refresh the display and have beautiful images move around for games and stuff. And the South Bridge is the slower speed for things that don't need that speed, like the keyboard, the USB, the hard disk, or take more time to move data back and forth. All right, and I wonder, is that door shut? Because we always have to shut the door. I found out why. Oh, yeah, that's why. This guy is famous. He's the head of the engineering department, and he's a famous troublemaker just like me. And he teaches an engineering class that is so much fun, the students always make a lot of noise. They're building robotic boats and slings and bombers out of wood and stuff and competing in the hallways. So it's noisy, but they have a lot of fun.
It's like living on premise.
What's that?
It's like living here.
Oh, yeah, yeah.
It's like a whole daytime.
Oh, yeah. But they have a lot of fun in that course. And that's why they make a lot of noise. And I've been accused of the same thing. The hackers have made enough trouble around here. Anyway, so, all right. So here's what you have. Your processor fetches an instruction, then decodes it, then executes, and then writes the result. And that's what happens in one clock cycle. Most instructions take several clock cycles, but that's the point. These are the steps of a process of an instruction being executed. I forget what it is. It's the first class, Intro to Engineering, and it's a lot of fun when Keith Miller teaches it. Anyway, so interrupts are a signal that something has to happen that will not wait its turn. Some special your processor is just reading this instruction, next instruction, then an interrupt says, nope, stop what you're doing and go do this other thing. For example, somebody pressed the off button. Well, shut down the system, forget what you're doing. That's what happens. So processors and threads, all modern operating systems have this. When you launch a program like Microsoft Word, that's a process, but the process contains threads. Every process has to contain at least one thread because threads are the units that actually get CPU time, but most of them have multiple threads, and the point is, if one thread is waiting for something slow, like the user to answer a box, other threads might be able to keep moving. Because this is a huge problem in computing. You have components that are thousands of times slower than other components. Like RAM is really fast, but the hard drive is really slow, and the network card is even slower, and the user's keyboard and mouse is even slower. So you could have something that could move waiting for something that is really slow. So you try to decouple them as much as possible so the fast actions can move. That's what threads are for. Now, multitasking is something that can run many programs at once, and all modern operating systems can do this. Multiprocessing means you have more than one physical processor, which is also typically the case now. Most people have 4 cores or 6 cores or 8 cores in their processor. Symmetric multiprocessing uses one operating system to manage them all. Asymmetric can have one operating system image per CPU. I've never seen that. Maybe that's what happens with cubes, though I'm not sure. Anyway, and so you can have a timer which notices when some critical process has hanged or crashed and reboots the system. Cisco routers have this. Cisco routers have a thing called check heaps that goes through every minute to see if anything's corrupt about the heap, and if it is, it reboots the system and starts over, which is why Cisco routers can be used for like 20 years, because even when they have serious defects, they will just reboot periodically and keep working, and the traffic will keep flowing with some loss, but they're very resilient. So CISC and RISC is another big difference. CISC is the Intel system where you have a large set of complicated machine language instructions. There are 10,000 machine language instructions in an Intel processor. They're incredibly boring. There's only about 8 fundamental instructions, like move data from here to there, but there's about 1,000 of them. Move data from register to register, move data from register to RAM, move from register to RAM plus register, move from RAM to RAM plus RAM, and just minor variations on the same thing over and over and over. RISC is the other way, where you do not have all these almost identical instructions. You have a small set of highly optimized instructions, and now your code will require more instructions, but the individual instructions will move faster. And this is what ARM does. And this is taking over. This turns out to get more done with less power and less time in practice in the modern world. Intel is gradually being replaced by ARM, as ARM seems to be more efficient. Yeah.
You figured out how ARM is different to save power?
Why it saves power?
Yeah.
It saves power for the same, because it's optimized, so it uses less power to execute one of those instructions than Intel would to execute one of their complicated instructions. That's all I know in just general description. I don't know exactly why. To understand why, you'd have to get down to how the transistors are laid up on the die. It's the geometrical layout of the transistors that determines how fast an instruction gets processed, and how much heat it creates, and therefore how much power it uses.
Because ARM is like RISC, RISC type machine.
Yes, it's RISC, and so that's the point. This is the theory. They said if you...
ARM is a lot more power.
ARM is a lot less power.
Yeah.
The battery lasts a lot longer. That's right. That's why portable devices almost all have ARM. That's why this Mac with ARM is much better than the Intel Mac. The battery lasts much longer, and it's much faster.
RISC was supposed to replace CISC
Yeah.
in the 80s with the Motorola.
It
and
was.
RPC.
They've gone back and forth. Intel pulled ahead. Right now, ARM, and it's not like there's a permanent...
Never took over.
Yeah.
And I think it's because CISC is just apparently easier to build.
Well, right now, ARM is taking over, I think, from Intel, but maybe Intel will improve their stuff and catch up again. There's a sort of a jockeying.
The less good one gets better, as
Yeah.
opposed to the better one replacing the less good one.
Yeah, yeah.
That's I thought the world was going to move from IDE to SCSI.
Yeah,
Didn't work.
That's
IDE
right.
got better.
that's right. That's right. So we don't know. And it's like, say, some people say ARM will take over the world like one student does. Other people think it won't.
No,
Anyway.
It won't is the two different types of processors. They deal with different types of data. So it won't-
Yep, that could be. Could be we'll just end up with both of them like we have now. Anyway, then there's direct and indirect addressing. You can add EAX 8 to EAX. So then you have EAX, you just add 8 to it, so the 1 goes in EAX changes to a 9. And this is a register. Then you can have direct addressing, where you add EAX to address location number 8. So it will take EAX, it will go to RAM and look at the contents of RAM location 8, which might have a 5, and then add them into EAX. This is where you directly address a memory location number 8. Here's indirect addressing, where you take EAX and you take this value and you interpret it as an address. So you look in EAX and find 12. Now you look in RAM location 12, and that's what you've found. And now you add that to EAX. These are examples. Now I see people saying, what will happen to quantum computing? Nobody knows. We're still developing the fundamental hardware for quantum computing. We're nowhere near having standards like this level for them. We just have a prototype quantum machines. And
I took a class in quantum computing.
Yeah.
But basically, in quantum computing, that's not the problem. To begin with, a bit is something that you can read and write.
yeah, and store data.
A qubit is something that
Right.
you can assign but never read, and that you can change,
Yep, and you have to be able to entangle it.
and that you can test
Yeah,
with some degree of certitude of whether or not your test is correct. So everything's different,
yes,
and so none of this applies basically.
that's right. Well, someday there might be CISC and RISC quantum computing, but we're nowhere near that yet.
It
Yeah.
does not apply in quantum.
No, not at all yet. All right, it looks like Apple's M2 have less performance power ratio. In some testing, yeah, but they're still better than Intel. EAX is the register stored on the processor. It's the fastest data storage unit on the machine is the registers, which are little memory locations on the processor. And you do almost everything by putting data in the registers, computing it in the registers, and then putting it out to RAM. All right. So then there's memory protection. This is something a student brought up in the chat a while ago. If you're running one program, it should be isolated from the other programs. It has its own memory region, and it's not allowed to write in another program's memory region in general. That's the point. And this is how you have secure multi-user, multi-processing systems. They separate the programs from each other. Yeah?
Remember a couple of years ago, there was the Spectra
Yep.
fall in the Intel?
Spectra and Meltdown?
Yeah.
Yes,
And-
yeah.
And the solution was your previous slide, the memory location, they put an extra bit, say, don't do speculation on those memories, and that's it.
They had to turn off, they had to limit speculative execution, which made the processor much slower.
Yeah.
Yeah,
And the solution was put an extra bit there to say no speculation.
that's right. Yeah, and that's why you'll see it if you're having to launch a VMware, it'll warn you this has that security feature turned on to resist speculative attacks.
Slow when it-
Yeah, it's slowed down cloud machines by a factor of 2.
Yeah.
My cloud provider gave you double RAM for free when that attack came out because it was the only way to keep their customers. It turned out that the latest improvement to make processors faster had a bad security consequence. So process isolation is what you're trying to do here. And so the logical control will prevent one process from interfering with another. You can do it with virtual memory, or object encapsulation, or time multiplexing, where each process gets different slices of time. There are various ways to keep the activity of one process separate from the activity of other processes. Here's another thing which will also confuse you. I found it very confusing at first. When you boot up a machine, it goes through the history of computing. It starts in a really old mode called real mode, which is for really old computers when they only had a tiny amount of RAM, like 32K and stuff. There's no process isolation. Any process can write anywhere in RAM. So it starts in that mode. Then it switches to protected mode as it boots up, which can handle larger amounts of memory and has isolation. x64 processor doesn't use segmentation. It uses memory paging instead. Anyway, it goes through series of ancient computing techniques during boot up. And if you listen to Paul's security podcast, he talks about secure boot up, which is mind-boggling. It's incredibly complicated. The process has gone through in a modern secure boot up. All right, so
Who was the guy again?
what's that?
Who was the guy again?
Paul's security podcast. It happens every Wednesday. I'm here for it. And yeah, Paul Asadorian is the guy, and he works for a company that is developing security products for the boot up process. So his team is all experts in the boot up process, and it is very complicated and very insecure now. There's a bunch of ways to attack it. Anyway, so virtual memory is the mapping between processes and hardware memory. This gives you isolation. It also allows you to swap pages onto the hard disk. So as you run out of RAM, you can take blocks of data and stick it on the hard disk in temporary files, and those are called swap files or virtual memory. If your kernel attempts to access memory and it finds that it's not really in RAM, but it's been put on the hard drive, it calls that a page fault. And now you have to stop and swap those two back up so you can read it. So the result is your machine runs more slowly when it has a lot of page faults. A lot of page faults mean you don't have enough RAM, and you're having to swap data to the hard drive. The BIOS is used when you first byte up the machine to do the post, the power on self-test. It checks to see what hardware it has. Do I have a hard drive? Do I have a floppy? Do I have a keyboard? Do I have a mouse? Do I have a display device? And because every time you turn off your machine, you might have plugged in more stuff. And when you turn it back on, it probes to see what stuff it has, and then decide which one of them it should boot from. If there's more than one boot device, it might have to ask the user which one do you want to boot from, and things like that. Worm storage is another way to do this. There are devices that can be written once but read many times, like CD and DVD. That's one way to make data that cannot be altered. And then the Trusted Platform Module is a term from the Orange Book. This is the military term for a required processor to meet military standards, and therefore it's included in all modern operating systems and hardware because you wouldn't be able to sell your stuff to the military without meeting the standard. So the Trusted Platform Module is a cryptographic coprocessor on a motherboard typically used for a Windows machine, although there's a similar one on Macs and also in the iPhone, where they call it a secure element. And this is a place where it hides things that you don't want the processor seeing. For example, if you encrypt your hard drive with BitLocker, there is a key that can decrypt the hard drive, and you don't want that key to be stolen, so it is stored in the TPM. And therefore, it is not in the address space of the processor at all. It's not anywhere in RAM. So no malware or any kind of attack could ever find it. It's on that chip, and the processor can never see it. What the processor can do is ask the TPM, please decrypt this stuff for me, but it doesn't have access to the key. And that's the point. It can do calculations and securely store the keys, and therefore you can use it as a hardware root of trust. So when you boot up, you can check to make sure the hash of what you're booting matches the hash stored in there, and that the operating system has not been altered. And this was supposed to end kernel mode rootkits. This is the secure boot up operation, which Microsoft has attempted many times to add to Windows, but it's never worked out. However, this is why iPhones don't have rootkits. iPhones do have a very secure boot up process, and they verify that the operating system you're booting is an official Apple operating system signed by Apple. So you can't run a modified operating system on your iPhone unless you jailbreak it. your iPhone is essentially impossible to infect with a rootkit. There's very little malware on the iPhone, and it tends to be very weak and easy to remove.
But the output from that cryptographic composites are decrypted data then?
Yes, you have to have some way to decrypt the data. Once you log in with your PIN or your password, then it's authorized, and then it can decrypt the data. But nobody can steal the key. So if you turn off the power,
But they can get the output data out.
yes, you can get, but the key is not in the output data.
Yeah, but you just want the data, you don't want the key.
Well, that's true, and that's why if someone steals your computer while it's logged in, they can get your data. But if you turn off the power and you leave your laptop on the airplane, it's safe because it's all encrypted, and nobody can get authorization to go to the TPM without your password, and nobody can get the key out of the TPM. That's why it's considered safe. By the way, it is possible to get the key out of the TPM. I think we might have, there's a couple of known attacks. One of them is one Joe Grand did, where he actually dissolved the TPM with acid and reached in with a microscopic probe to find the key, and he destroyed 100 chips, but he managed to make it work once. So that's not completely impossible, it's just almost impossible.
So the key is buried into the composite?
Well, it's stored in there, in memory, but if you could sense the right pin, you could actually see it go by. He managed to find it, yeah.
So they all contain the same key?
No, it's generated randomly for each machine, yeah.
So the one he found only worked on that computer?
Of course, yes. And so that means if you had a laptop powered off that was encrypted with BitLocker and you really wanted to get in, you would have to do something heroic like that to get in. You would have to like physically dissolve the plaque through this chip and feel around to power it up and find the key in there. It's not completely impossible, it's just very, very next to impossible.
And what prevents an unauthorized user to use that key? You say you need the password.
They need to have the password. Yeah, they need to have the password to.
Because I'm guessing the TPM isn't complete. You also need the password.
That's right. There are layers of encryption. Yeah, you also need the password, which is used to generate some key, which enables you to send the commands to the TPM.
Otherwise, I'm guessing it will give you a false decryption.
Right.
From garbage.
Well, it will refuse to decrypt because you're not authorized. Yeah, that's right. And if you look at the iPhone boot up, it has like 5 different layers of encryption for this reason. Every module has its own key, which is unique to go to the next one. Right, see, Apple M1 chip already got jailbreaked. Yeah, that's right. There are jailbreaks. If you jailbreak your phone, you turn off all this protection. And then you can do unauthorized things. And then, of course, you no longer enjoy this security from malware. All right, so data execution prevention has been around since about 2002. This is the ability to mark areas of RAM non-executable. Before, there were not permissions in RAM. Now, when you allocate a memory region for use by a program, you can specify what permissions are on the RAM, and you can mark RAM non-executable. This prevents buffer overflow attacks, which we're doing in CNET 127, where you would put in something like a password or username, and you would embed code in it, and then you jump to that code and execute it. This is how buffer overflow attack works. But now, no area of memory is allowed to be writable and executable at the same time. That's the standard rule. And so if you can change it, you can't execute it. And therefore, if you feed in data, it's not executable. That can be done. Now you can turn it off, and that's what some attacks do. And there are other attacks that take over the machine without directly executing the code, just reading it as addresses. So there's always some way around it. But this did end an entire generation of viruses, all the ones that affected, say, Windows XP. They added this to Microsoft in Vista. All right, and ASLR is another thing they added in Vista, where in the early days of computing, meaning Windows XP and earlier, you would just, if you loaded a program, you double-click something like Microsoft Word, it would just find the next available memory and put it there. So the operating system would boot up, and that'd be the first 32 megs, then your antivirus would be another 16 megs, then you'd have your browser, and then your Microsoft Word and stuff, and you could pretty much guess where you were. And therefore, if you injected code and tried to run it, you could guess where you are in memory. So to prevent that, now, every time you launch a new process, it randomly locates it in memory. And if you close it and launch it again, it randomly locates it again. This stops attackers from knowing where they are. So even if I inject code, I can't figure out what address it has to jump to it. And this, again, helped stop a whole generation of viruses. There are ways around it, but it ended viruses up through about 2002, whole category ones that based on this technique. All right. So let's look at 3C. Yeah, and if someone points out the M1 got jailbreak. Yeah, you can jailbreak a lot of machines, like Chromebook and stuff. You can turn off these security features, and then you get the ability to do unusual things with your machine, but of course you then become vulnerable to malware. And so that's why if you do that, you avoid your warranty. If you jailbreak your phone, Apple does not want to hear from you anymore. They don't want to help you anymore. They say, well, you ruined everything. Yeah. Yeah, that's a reason you probably want to jailbreak your Samsung just to get all the crap off it. Yeah. It's rooting it, yeah. Yep. Yeah, it'd be nice. Yeah, they supposedly try to prevent you from doing that, but there are probably ways around it. Yeah, that's good. Good. Well, good. I'm glad to hear it. Yeah. All right. Okay, I guess I'll wait a few more seconds. We got 16 and 2. Got half the people. That seems about all we usually get. That's right. That's the other problem. The Androids are often not updated promptly, which is really bad. So the manufacturers often leave you vulnerable for months or years at a time. Yeah. All right. So what CPU ring is user mode? Yep, they call it ring 3. Ring 3 is the low privilege mode for user mode. All right, users can't handle the truth, so your computer lies to you. What's that? That's abstraction, where they just show you a simplified cartoon of the situation, not all the complicated details. Same problem at management. Management usually doesn't really know what's going on. They only have a simplified summary of what's going on. All right, so a communication channel between components. All right, that's the bus, data bus. All right, I launched Microsoft Word, so what have I created? Yeah, you created a process which will then contain one or more threads, but the thing you immediately create is called a process, and you'll see it in Task Manager. All right, what's the cryptographic coprocessor? A second processor on the machine. All right, that's the Trusted Platform module to meet the Orange Book requirement for a trusted platform. All right. All right, here you go. And Billy is one twice. And Buhani is one twice. All right. So let me stop this recording and we'll take a 10-minute break.